Hello, everyone. We are Thursday today, and we are going to continue where we left off yesterday. So I was trying to do matrix multiplication yesterday, but then I went down some rabbit hole of like lower level compilers, memory, all of that, and I still want to quickly review how that works. Specifically, I took a class CS241, I think, yeah, which was like our compilers course, right? How we go from bits, I guess, to programs. And the thing that I was confused about, we had an OS class where we learned about when you have an interrupt, uh, like when you context switch from one process to the other, you need to store, um, like what are the things you need to store? Like you store your stack frame, but I'm confused. I was confused on like what the stack frame was. This stack, like this control stack. So this is a kernel stack, right? So you save the context of your process, and I guess that's stored in a process control block. Um, so that happens at process level, but within a process, you also have a like some sort of stack. But I was confused yesterday why I was talking to ChatGPT and it was saying how the stack pointer. Why does the stack pointer go downwards? What does even mean? Like I'm kind of confused on that because it stores at the top of the stack, right? And then like how does this look like? Um, chunk like instead we chunk. Does the stack grow upward, upper? Yeah, this is what I need to review. I don't know what I mean here. Honestly, it's been too long. I don't think this is a good explanation. Application binary interface. What the hell is that? Like I've seen this word, but I don't deeply understand what it is for. That doesn't mean anything. Like I don't understand. how an ABI is like. How is it different from just a binary? Yeah, like a binary is just compiled machine code that a CPU can execute, right? Uh, yeah, like when you link, is there an ABI? But some abstract concept in the ad example. What does the dot so look like? It's a little confused. Right, so in my head, there's functions that exist at different memory locations. Um, so I thought you just like change your program counter to be at that memory address. Um, so where does the stack come in? The stack comes in when you want to pass, right? Function calls can take in arguments, which take in your values, right? Um, so downs is other bookkeeping information, like where function. Yeah, and inside a function, you might create new variables, right? Um, so stack pointer.
I built this simple computer and wrote a clock cycle. We see it writing that F routine so that we can continue executing our program. And so what address does it need to jump back to? That's the question. Because the return from subroutine doesn't give an address. It just says return from
Hmm.
the world. And see, printing character by character here, it's very repetitive because I just copy and pasted the code to print each character over and over again. And then if we go all the way back up to the top, I'm doing the same thing at the top here just to send the
Might watch this
instructions
video.
as a display module setup in the first place. So let's simplify this by moving this code here for sending an instruction into a subroutine. We can just call it with a single line of code each time we need to. So I'm going to copy all of this and paste it way down here at the bottom of the program. So this is all the way at the bottom. I'll paste that same code. And I'll add a label here called LCD instruction, except I'll spell it right. And I'm calling it LCD instruction because this is the code that sends an instruction or whatever instructions in the A register to the LCD module. So back up at the top here, here we're sending some instructions. We're loading the instruction into the A register. And then instead of having all this code here, we just say JSR, which is jump to subroutine LCD instruction. So this will load the instruction into the A register, and then jump down to the bottom here to this LCD instruction section here, and execute all this code here, which actually sends that instruction to the LCD. Then at the end of this, we can say RTS, which means return from subroutine, which will exit the subroutine and then jump back up wherever we came from. So if we go back to the top here, that'll jump up here to where we just finished this jump subroutine instruction. And the nice thing is that we can reuse that subroutine for each of the instructions we need to configure the LCD. So instead of doing all this, we get rid of that and say JSR LCD instruction. And then same thing here. This is another instruction, so we get rid of all that and add another jump to subroutine LCD instruction. And so now it's easier to follow this code because here, this is all the code to initialize the LCD module. And you can check out my last video where I go into what each of these instructions do and what each of these bits are for. But if you watch that video and know what these bits mean, then hopefully this code is pretty clear about what it's doing. And of course, I've also got the comments over here, which should help, assuming they're correct. And then of course, we can do the same thing for actually printing the letters. So all of this code here prints the letter H from the A register. So I can copy all that down into a subroutine down here at the bottom as well.
Yeah.
Section here, and it prints Z here. Back up at for each letter. Then it's a lot shorter machine code that runs. So let's save this. Now if we look at the machine code we started with, this is all the assembled machine code. You can see there's a fair amount of it. Now let's run the assembler on our modified code. And now if we look at the new code that we generated, see this is a lot shorter. So that means it's also going to take up a lot less room in the ROM or wherever we're running it from. Now I guess there is a trade-off in the sense that jumping to and returning from the subroutines will take a few extra clock cycles to execute. So technically this code will run slightly slower than what we had before, but there's a huge improvement in size. So I think that's a fine trade-off to make. So now I've got the EEPROM in the programmer, and this is just writing the new code to it. And it's done. So let's put the EEPROM back in the circuit, and it should work the same as before because we haven't changed the functionality at all. We've just factored out that repetitive functionality into subroutines. So I'll power this back up, and then I'll reset it here. And it should work just the same as before, and we should see it print hello world on the screen, although it looks like maybe it's not working. I'll try resetting it again. And yeah, it's not working. So what's going on here? Well, what we can do is step through the program and try to see what's going on. And in order to see exactly what's happening, I'll connect up a bunch of pins from this Arduino Mega that I've used in some of the previous videos. And so here I'll connect 16 pins from the Arduino to 16 address lines, which will let do the 8 data line, and all here to the, got the of course how it works. And this is the same Arduino code could be hooked up. Yeah, there it goes. So it's definitely doing something. And this first column here tells us, hey, in the serial monitor here, this is the first 16 wires that I hooked up there. It shows us the address bus. The next 8 bits here, the second column shows us the data bus. And then we've got the address bus here just in hexadecimal, and over on the right, this is the data bus in hexadecimal. And then this column here is either R or W to show whether the processor is reading or writing to the data bus. So let's hold down reset now, and then just stop the clock. And then I can clear the output here. And then it takes 7 clock cycles for the processor to initialize, so I'll step through 7 clock cycles. And incidentally, when I made the circuit to do the single stepping, I think I may have made the pulse width a little bit too short, so it still does sometimes bounce when you let go of the switch. A quick hacky workaround is just to put a 0.1 microfarad capacitor right across the switch, which I did here, and that seems to help things a little bit. But in any event, after that initialization, it then reads the reset vector. It gets 8000. So it's going to jump to address 8000, which is the start of our program. If you didn't follow all this, that's fine. I cover all this in the first few videos if you want to go back and watch that. But at any rate, at this point, we're at address 8000, and we're reading A9, which is the first load A instruction, because A9 is the opcode for load A. So to keep going here, we get load A, FF, and then 8D is store A, and so that's store A 6002, and that's this store A DDRV. And so then on the next clock cycle, we see it writing the FF to address 6002. If we keep going, we get load A E0, and then store A 6003, so that's the store A DDRA. And now we can see it writing that E0 to address 6003. The next we get load A38, and that's our first instruction that we want to send to the LCD. So far so good. And now we're reading 20, and that should be the jump to subroutine. And if we look at the data sheet, that is indeed correct. 20 is the opcode for jump to subroutine. Okay, so then next we expect it to read the address to jump. So it's reading 5D, and then 5D again. But this is sort of interesting. So for some reason it's now at address 0124. It's reading, and it's I don't know where it's getting this 5D from. But after this jump to subroutine, I would expect it to read 2 bytes. I would expect it to read a byte from 800D and 800E because that's where the address to jump to is. But instead, it's going to this 0124, which is sort of weird. So let's keep going. So wait a minute, now what's it doing? So now it's still at that address 0124, and now it's writing, and it's writing 80. And then if we go one more clock cycle, now we see it's at address 0123, and it's writing 0E. So what's up with this? We have this jump subroutine instruction, and then it seems to have read half of the address to jump to, but then it's going into these other addresses, and it's looks like it's writing something to those addresses. So what's up with that? Well, let's actually keep going a couple more steps. So if I go one more step, it actually seems like it's maybe back on track here, right? Because we had 800C, it's reading the opcode for the jump to subroutine. Then 800D, it's reading 5D, and then 800E, eventually, after all this weirdness, it's reading 80. And that part seems right, because we have a jump subroutine, and then if you look at this 5D and this 80, that's the address it's jumping to, and those are the next 2 bytes after the instruction. So that sort of makes sense. Jump subroutine to 805D, that sounds right. And in fact, if we go one more step here, we end up at address 805D, which is the actually beginning of our subroutine. So this is doing the right thing, but it's doing something else kind of weird here with this address 0124, and it's writing some data there. So what's going on with that? And what it's doing here, particularly these 2 clock cycles here, is actually really important, because we're jumping to a subroutine. And the way we expect this to work, if I go back to the code here, we are at this point here. So we're doing this jump subroutine to LCD instruction. And LCD instruction, apparently the address for that is this 805D. And we are eventually reading that, right? So we're reading the jump subroutine instruction. So that's the jump subroutine here. And then the label or the address to jump to
You
is
start
also
with
the
the current
instruction. And so we read
context
that, the instruction is
into your stack
800C,
frame,
so
right,
it's
or
going to
something
read
like that.
800D and then eventually 800E to get that address 805D, and then it jumps to 805D. And then 805D is LCD instruction, so that's all the way down here. So this LCD instruction, the first instruction there should be store A. And so if we look here, 805D, we're reading an 8D, and 8D is in fact the opcode for a store A. But what's going on here? What's going on here in the middle? What is this writing? What is this 0?
You have 2 clock cycles to store
well, what's going on is once we get down to this LCD instruction, we jump down here, we're going to start executing all this stuff, and then eventually we're going to get to this return from subroutine, and we're going to need to somehow find our way back up to where we started, up here when we called that subroutine, so that we can continue executing our program. And so what address does it need to jump back to? That's the question, because the return from subroutine doesn't give an address, it just says return from wherever you came from. So the processor actually has to keep track of where we came from, and that's what it's doing with these extra clock cycles here. And specifically what it's doing is it's writing this 800E, which is the return address that we're going to have to return to.
Yeah.
This 800E is actually the last address that we came from. So what the processor is doing is it's taking a couple extra clock cycles here to save that address so that we can return back to it. And so it's writing this 800E.
But if you have nested function calls, it might clobber.
So at this point, we're in the subroutines. We read a store A 6000, this port B, and we see it write the instruction to address 6000. We have a load A0 and a store A 6001, which is port A, and there's the 0 being written to 6001. And we have load A80, which is the enable bit, and a store A to 6001 again to set the enable bit. And there it goes. We see the top bit here getting set to that address 6001. Then a load A0 again, and another store A 6001. And then we see the 0 going out to 6001 again, clearing that enable bit. And that's the whole sort of dance we need to go through to send an instruction to the LCD, like I talked about in the last video. And so that all seemed to work just fine. And so here we are at the next address, 806F, where we're reading 60 hex. And 60 is the instruction for return from subroutine. So what do we expect this to do? Well, it should jump back to that return address that we saved up here, this 800E. So we'd actually expect it to jump to 800F, which would be the next instruction to execute after the subroutine. So it should somehow jump back to this 800E. So let's keep stepping forward and see what it does. So if we step forward, it actually doesn't seem to do anything. It just kind of advances to the next, after 6F, it goes to 70, which is just the next memory location. And it's reading, this 8D, which I guess is whatever instruction is there. I don't think it's actually reading this to execute that instruction. I think the processor is actually just taking a couple extra clock cycles here, to do some internal stuff. So I don't think that just because we see this on the bus that it's actually going to try and execute that. And if we keep going, we see now it actually is reading from address 0122. The next clock cycle, it reads from 0123, and then 0124. And if you remember, that 0123, 0124, that's where this return address was saved. So up here, when we actually jumped into the subroutine, the processor saved that return address at address 0124 and 0123. So I saved that 800E. And so now down here, it seems like it's trying to get that return address back so that it can return, which makes a ton of sense. But we've got a problem. And the problem is that it's not reading that same address back that it saved up here. So it saved this 800E by writing it to those two addresses. But down here, when it reads from those addresses, it's just reading this 8D. And this is our problem. This is why our program doesn't work. And the problem is that we actually don't have any hardware that responds to address 0123 or 0124. There's nothing at this address. So when the processor writes to address 0124 or 0123 up here, it's not actually writing to anything. It's just sort of throwing it out on the bus, but nothing. There's no hardware responding to it. There's no memory. There's nothing that's doing anything with that. And so then when it tries to read it back down here, it's not actually reading from anything. It's just getting whatever happens to be on the bus. And that's why our program doesn't work. The processor is trying to save the return address, but our computer doesn't actually have any RAM in it yet. So it doesn't work. And so it gets this far, but when it tries to return from the subroutine with this return, 60 instruction, it tries to read the return address, and it gets this 8D. And if we step once more, you can see it jumps to 8D. So it thinks it's jumping back to where it should, but it's not. It's jumping to some other just sort of arbitrary address. It's definitely not going to be our program anymore. And so if we keep going, it's just going to do all kinds of other weird and wild things, but none of this is anything that we want. So one question you might be wondering is, why is it trying to write the return address to 0124 and 0123? Where did 0124 come from? Where did 0123 come from? Where did these addresses come from?
The stack pointer?
Well, the datasheet for the processor, it says the stack may use memory from 0100 through 01FF. And this is something that's just hard-coded into the way that the 6502 microprocessor works, is these particular addresses are reserved for this thing called the stack. And the way that a stack works is you've got these 256 addresses from 0100 through 01FF in memory, and then you've also got a processor register called the stack pointer that is pointing to one of these addresses. So this is actually going to be an 8-bit pointer, but if it has a value of 24, for example, then it would be pointing to this address 0124 because all of the stack is going to be 01 something. So if the stack pointer is 24, then it's going to be pointing to 0124 in memory. And then when we do that jump to subroutine, it pushes the return address onto the stack. So we're going to put the return address of 800E onto the stack. It's a 0. But then also, each time it pushes a value onto the stack, it decrements this stack pointer. So now their stack pointer is pointing up there. That way, if we're inside one subroutine and we want to call another subroutine, we can push another return address onto the stack and kind of keep going and keep calling all sorts of subroutines. We can even push our own data onto the stack, as long as we're careful to pull it off the stack in the opposite order that we push it on. The stack can actually be a really handy place to temporarily store data. So for example, with our subroutine here to send an instruction to the LCD, the subroutine starts by, we actually load something into the A register and then call the subroutine. And if we look at the subroutine, it's going to use this in the A register.
That's what you mean when it goes downwards. the drawing here. We'll just like use Ben Eater's example, I guess. Yeah, I should have remembered this when I took my CS241 class.
That way, if we're inside one subroutine and we want to call another subroutine, we can push another return address onto the stack and kind of keep going and keep calling also works subroutines. We can even push our own data onto the stack, as long as we're careful to pull it off the stack in the opposite order that we push it on. The stack can actually be a really handy place to.
I like what gets pushed to the stack. I literally have procedure. Oh my god. See, this stuff, I definitely learned this, but I really did not fully understand this. Or maybe I did, but I forgot how it worked. But yeah, this stuff's kind of important. So your stack grows downwards because as you increment the stack pointer, you actually decrease in memory address, right? But each time you have a new function call, you will push you need to keep track of like the program counter to resume from that function after the stack is destroyed.
Temporarily store data. So, for example, with our subroutine here to send an instruction to the LCD, the subroutine starts by we actually load something into the A register and then call the subroutine. And if we look at the subroutine, it's going to use what's in the A register, oops, this one here, but it's also going to overwrite what's in the A register in order to toggle the enable bit here. So something to be aware of is that up here, where we call this subroutine, we're loading something in the A register, and then we're calling the subroutine. Well, when that subroutine is done executing, this value is not going to be in the A register anymore because the subroutine modifies it. And in our case, that's fine. We're putting something else in the A register right away anyway.
But
So
we need to
it doesn't matter. But if we want to, down here in the subroutine, what we could do is push the value in the A register onto the stack. And then what that would do is it would put that value, I think it was 3.8 or something.
So that's why when you compile code that pushes, when you do function calls, you will push to the stack first because someone else called this function, and you want, before overriding those values, you want to save the current context onto the stack. This is fundamental knowledge. When you push something onto the stack, you need to make sure that when you try and look inside Gitbo, when you look at the assembly code for a function call, the first thing is called is always pushing context to the stack pointer, because after you exit the function, you want to make sure you restore those values.
And then decrement the stack pointer again. And so we have this extra value for what our A register was when we called that subroutine. Then of course we have to
add things, actually decrement. When you remove, you actually decrement. You did this.
be very careful that before we return from the subroutine, we need to pull that value off the stack and put it back into the A register. And so what this pull A will do is after we've used the A register to toggle the enable flag here, it'll pull a value off the stack, which in this case is going to be this 38. It's going to pull it off the stack and it's going to increment the stack pointer. And then that 38 will get put back into the A register here. So by pushing the A register onto the stack at the beginning of the subroutine and pulling it off the stack at the end of the subroutine, that means that when we call the subroutine up here, when we do this jump to subroutine, when we get to the next statement here in our program, the A register will have the same thing that it had before we called the subroutine. If we cared about that, in our case, we don't actually really care about that. So I'm going to go ahead and delete both of these lines because they do add a couple extra clock cycles to the program, and there's just no need. If we push A onto the stack and don't pull it off before the return here, that would be bad. Because instead of returning to the correct address, 800E, if the stack pointer is off, because we didn't pull the top value off the stack, then the return instruction would think we need to return to 0E38. So we'd end up jumping to some other random memory address, 03E38 or whatever. And of course that wouldn't be good because who knows what's at that address. So we always have to be careful about not pushing stuff onto the stack that we don't pull off later in the reverse order. We also have to be careful because on the 6502, like I said, the stack always starts at address 0100 and goes through 01FF. So it's just 256 bytes. So if we end up pushing more than 256 bytes on the stack, if we're calling more functions. So we call this function, maybe we push this value on the stack, and maybe within this function we call another function, and so we have to push another address onto the stack, and maybe that function calls another function. If we got convoluted enough, or maybe we have some recursion or something, we could get in a situation where we keep pushing more and more stuff onto the stack, and then of course we get up to 0100, and then if we were to decrement the stack pointer, we just wrap around FF, and so we'd end up down here at 01FF, and we could keep pushing stuff onto the stack. And all of this would be fine up until the point where the stack pointer wraps around and we're about to push something onto the stack that overwrites stuff that we already have on the stack. And if that happens, that's not good. That's what we call a stack overflow. Because here, if we ended up pushing something else onto the stack, maybe there's another function call, we've gone down the rabbit hole here, and we have another function call, we push that return address onto the stack, it would overwrite this return address. And everything would seem to be working fine because we would return from that function and
it's just a custom portion of memory that we to manage our program. It helps keep track. Keep track by the program counter as is a logo that might be used. You don't want to clobber. Stack is a special function calls local data and yes. The compiler does all this work. Need to worry. Okay, what's the frame? The stack pointer doesn't actually store the function instructions, right? The function code actually is somewhere else in memory. And it just stores the memory of where function code begins. Code is data. So what you say? Code is data. Can you Oh, I see. Probably should. Okay, I think this Ben Eater drawing is not that great then. Stack goes downwards. Alright, So we want, you can do this. .186, 189, and your stack pointer stack grows downwards. High address, low address. High address, low address. High address. And then there's like a rectangle. This is like right. That, I think that would make sense. Yeah. You redraw this where the high top. Oh, sorry, I got distracted. The picture has top as lower memory. Will use higher top. Yeah, because it actually goes downwards. Why? Like heap memory extends the function call. Alright, so you can allocate heap in a function, and then after you exit the function, that data is still there for you. Whereas in a stack, I guess you don't explicitly have, you don't explicitly use the data, but you don't have a guarantee, right? Because it might be overwritten or like restored from your previous function call. And the compiler does the job of like optimizing that. And when you inline it, you no longer have to do a jump, in which case you no longer have to like store values onto a stack pointer and then use the register or something else. Like you will just inline the function call. Great. Okay, I understand. Maybe you guys don't understand. Why did he goes upward? Is there a heap memory per process, or it's a general OS thing? So I guess there's similar ideas, right? Like in the context where you switch between processes, you're not worried about clobbering registers, but you need to know like what where your current program counter is for the current process. Um, oh, it's not okay. I don't know what the map is. Wait, my friend just told me leak seek plagiarism. What did they plagiarize? Like This is ridiculous.
So here is where President Trump stands on China possibly pulling ahead in the AI race. Watch this.
Carolyn, you say restore U.S. dominance. Is there a fear that the U.S. either
technology that the models are basically producing things like Black Hole Washington, and I think that when you're complacent.
Honor data. What's the BSS? Your register, that is the program counter. Okay.
And we would return from the right address, and we return from whatever called in, and we pull off whatever else we had on the stack, and we just kind of keep wrapping around. So we got to FF, and then when it incremented, and we pulled something else off the stack, it would wrap back around to 0, 0, and we keep pulling stuff off the stack. All of this would work fine until we get to this point where we've overwritten stuff from that very first function call. And so when we return from that very first function call, we wouldn't have the correct return address here, and that would be bad. And who knows what would happen. So we definitely want to be careful to avoid a stack overflow situation like this because they can be very difficult to troubleshoot. And you might also be wondering, we've got this stack that goes from 0100 through 01FF. Why do we start pushing data at 0124? Why would the stack pointer start here and not anywhere else? Well, it's because the stack pointer just happened to start out at 24. It just happened to be initialized with that value. It's just completely arbitrary when the CPU powers on what value is going to be in that stack pointer. So maybe a good thing to do would be at the beginning of our program, or right when the CPU powers up and initializes, to initialize the stack pointer to FF here. So it always starts out at the top of the address range.
Oh yeah.
And the nice thing about that is that as we push values onto the stack, we always look at the stack pointer and know, like, oh, it's pointing to, the stack pointer is 26, it's pointing here. Then that means that we would have, 26, or not 26, but 26 hex, however many bytes that is. We would know how many bytes we have left in the stack. Whereas if it's down here at, FD, we know we have 254 bytes available above that in our stack. So how do we go about putting FF into the stack pointer to initialize it like that? Well, if we look at our instruction, there's a load Y instruction, but unfortunately there's no load stack or load stack pointer instruction. However, there is, if we flip over here, there are some transfer instructions that work with the stack pointer. So for example, we have transfer X to stack. This will let us put a value in the stack pointer from the X register, which we can load. So basically this has to be a two-step operation. First we can load X with FF, and then transfer X to S, and this will end up initializing the stack pointer to FF, because we're loading that into X, and then we're transferring that to the stack pointer. And that'll initialize the stack pointer to FF, meaning the stack pointer now starts at the end here, and then as data gets pushed onto the stack pointer moves up like this. Although, usually say the stack grows downward because the numbers are actually getting smaller, so maybe I drew this upside down, but you get the idea. But anyway, the reason our program isn't working is because it's trying to use this stack, but our computer doesn't actually have any RAM in it at address 0123, 0124, or 01FF, or anywhere. And that's what I plan to fix in the next video. I'll add some memory to the computer by wiring up this RAM chip. And right now, of course, we have the ROM, which is read-only memory, and that's where our program is stored. But so far, we haven't added any RAM we can read from and also write to. And so that's what we need to do. So in the next video, I'll add the RAM and make sure part of it is accessible at those address 0100 through 01FF. And then our computer will have memory we can write to, which means it'll have a stack, which means that subroutine calls will work. Up here, when we call that subroutine, so that we can continue executing our program. And so what address does it need to jump back to? That's the question. Because the return from subroutine doesn't give an address, it just says return from wherever you came from. So the processor actually has to keep track of where we came from. And that's what it's doing with these extra clock cycles here. And specifically what it's doing is it's writing this 800E, which is the return address that we're going to have to return to. Because this 800E is actually the last address that we came from. So what the processor is doing is it's taking a couple extra clock cycles here to save that address so that we can return back to it. And so it's now at address 0124. It's reading, and it's
so this thing doesn't have any RAM. So how is it doing anything?
It's 5D from. But after this jump to subroutine, I would expect it to read 2 bytes. I would expect it to read a byte from 800D and 800E because that's where the address to jump to is. But instead, it's going to this 0124, which is sort of weird. So let's keep going. So wait a minute, now what's it doing? So now it's still at that address 0124. Now it's writing, and it's writing 80. And then we go one more clock cycle. Now we see it's at address 0123, and it's writing 0E. So what's up with this? We have this jump subroutine instruction, and then it seems to have read half of the address to jump to. But then it's going into these other addresses, and it's looks like it's writing something to those addresses. So what's up with that? Well, let's actually keep going a couple more steps. So if I go one more step, it actually seems like it's maybe back on track here, right? Because we had 800C, it's reading the opcode for the jump to subroutine. Then 800D, it's reading 5D, and then 800E, eventually, after all this weirdness, it's reading 80. It doesn't give an address, it just says return from wherever you came from. So the processor actually has to keep track of where we came from. And that's what it's doing with these extra clock cycles here. And specifically what it's doing is it's writing this 80 back to that return to do some internal stuff, in a sense, throwing it out on the bus, but nothing program anymore. And so you've got these 256 addresses from 0100 to 01FF in memory. And then you've also got a processor register called the stack pointer that is pointing to one of these addresses. So this is actually going to be an 8-bit pointer, but if it has the value of 24, for example, then it would be pointing to In my last video, I optimized this assembly language program quite a bit. It just prints out hello world, but it was over 170 lines long because it had tons of redundant code that I was able to remove by factoring it out into a couple subroutines. But then when we tried running the program, it didn't work. And as we saw in the last video, it didn't work because when the computer jumps into a subroutine, it pushes the return address onto the stack, which is in memory, and then at the end of the subroutine, it pulls that return address off the stack so it can jump back from where it came. Now, our problem is that our computer doesn't actually have any RAM in it at address 0100 through 01FF, where the stack needs to
I
be,
see.
or anywhere else for that matter. So let's fix that. Let's add some RAM. So this is the 62-256 parallel RAM chip, which the 256 in the name indicates that it can store 256 kilobits, which with 8 bits per byte means we get 32 kilobytes of data. So let's hook it up. And right now I'm just disconnecting the Arduino Mega just to get that out of the way. We can reconnect it later, but just to make it easier for you to see what's going on, I'll get it out of here right now. And now if we look at the pinout for this RAM chip, we see it's actually very similar, in fact, almost identical to the ROM chip we have, which is very convenient. Because just like the ROM chip, it's got 15 address lines because it's also 32. We have 32K ROM and then a 32K RAM, and it's got the 8 data lines, and the pinout is actually exactly the same. So if I want to connect the RAM chip here to the data bus and the address bus, really I just need to connect all the data lines over and all the address lines over. So that way the RAM chip is hooked to the address bus and data bus just the same as the ROM and everything else.
How does RAM work, I guess, right? Like, the computer does a read from some memory address, right? That's a CPU. I saw this today, this pipelining, right? Like, so you have an instruction that can also read data. If you read data, there's data memory, and that will write it back into a read register. Is that what's happening? Like there's a RAM module that's...
Then I'll connect the address lines and the data lines. So I'm hooking up 15 address lines, A0 through A14. And of course we already have these connected from the microprocessor, A0 through A14 hooked to the ROM, A0 through A14. And now I'm just hooking them, those same A0 through A14 lines over to the RAM chip. Okay, so those are all the address lines connected. Now I just need to hook up the 8 data lines. And same thing here, we've got the 8 data lines, of course, already going from the microprocessor to the ROM chip. So I'm just extending those same 8 data lines over to the RAM chip. And there we go. Now we've got all of the 15 address lines plus the 8 data lines hooked up. So we've got all of our address and data lines, plus, of course, our power and ground. And the only pins now that are not hooked up are the write enable, the chip select, and the output enable pins. So that's write enable, output enable, and chip select. Those control signals we need to hook up as well. So write enable is pretty easy because that hooks right to the read-write pin on the microprocessor. Because the microprocessor has a read-write signal that it outputs along with the data bus to say whether it's reading from the data bus or writing to the data bus. And that goes low when it's writing, and then the write enable is an active low here. So we can just hook that write enable signal from the read-write signal from the microprocessor over to the write enable input over here on the RAM chip. There we go. So that's the write enable pin. But how about output enable and chip select? Well, when do we want the RAM to actually be active? Well, we only want it to be active when the microprocessor is actually reading or writing from some address that's within the range for the RAM. And of course, we know we want that to include our stack, which is 0100 through 01FF, but we want a larger range than that for RAM. So this is the memory map that I've come up with for the computer right now, where we've got the addresses, because there's 16 bits of address coming off the microprocessor, so the address can go from 0000 through FFFF. And right now the way we've got this hooked up is the ROM chip is taking up the upper half. So anytime that most significant address bit, address 15, anytime that is high, then the ROM is active. And so the ROM is taking up addresses from 8000 all the way through FFFF. So the easy thing to do would be just to have the RAM enabled whenever the ROM is not enabled. That way the RAM would take up the lower half of memory and ROM would take up the upper half of memory. The only problem with that is that we need to have some address space here for I/O. And in previous videos we have this versatile interface adapter hooked up here on address 6000 through SIP loading is easy. Because we've got the output enable, which is active low, and we've got the chip select, which is active low. And in order for the RAM to actually output anything on the bus, both of those have to be low. So if we hook output enable to address 14 and we hook chip select to address 15, then the RAM's not going to output anything unless we're in, again, we're in that range of, that we want the RAM to be from 0000 through 3FFF. Now, technically, if address 14 is high and address 15 is low, so we're in this range, then output enable wouldn't be active. So the RAM would never output anything on the bus, but potentially, if the processor is writing to an address in that range, it would actually write to RAM. But we don't really care about that because we'd be writing to a part of the RAM we're not using. So that's fine. So this seems like it would be a pretty good approach. Just hook address 14 from my processor up to the output enable signal and hook address 15 up to the chip select signal. And this should ensure that the RAM is active only in this address range. But not so fast. All this sounds good, but of course reality is always a bit more complicated. If we look at the datasheet for the 62256, the RAM chip, it's got these timing diagrams that show various limitations in the timing of signals when doing a read or write under various circumstances. And the 6502 processor also has timing diagrams that show various limitations. And we ought to take some time to study these timing diagrams to make sure we understand what those various limitations are to make sure that we're meeting them. Otherwise we could end up with some really hard to debug problems down the road. For example, this is the read cycle timing diagram for the RAM chip that we're using. And what it's showing us is it's showing us how we would actually do a read from the RAM chip. And you think about how a read would work. You think, well, okay, the microprocessor wants to read some data from the RAM. And so what it's going to do is it wants to read from a particular address. So it puts that address out on the address bus, and that's what these green wires are. And so those are hooked up. We hook those up to the RAM. So the RAM's going to have that input there from those addresses. And what a bit.
Yeah, I'm not listening to this. I think I understand. What is it? What is BSS? You can just do size. There's a procedure, and then there's a nested procedure. Where did I see the keep memory management? Is that no? Where did I see that? I saw. Dude, where was that thing I saw? No, I definitely saw it. Keep memory? I swear I did not see. Oh, Newman architectures. MIPS. Closure. Oh, closure. Because I also saw stack in CS 137, when my teacher first introduced programming memory, you had the stack and the heap. Oh, your code, your global memory. 5 sections of memory, and you have your instructions. Oh. I see. And you have code. Well, your stack goes downward, so usually you can think of it as higher memory addresses and lower memory addresses. And what you have is the stack pointer. So your stack, this will keep track of your local variables when you have function calls. When you call a new function, push um, you'll actually push whatever variables. See, that's I'm not sure. When you push to the stack, you push the of your current function, not the function going into, right? Yeah. Context, not the of the things that you are going into. Then aren't you also allocating stack memory to the next function call? Like you need to know how many local variables it's using. Varicals. Why calling it bar push is its own. Main calls too. Yep. You know, when I was doing this, I did not have ChatGPT. I think this makes it so much easier to learn. Okay. I think I understand. There is a Marie. Okay. I think I understand. It goes downwards. Endianness just determines how you read the bytes, right? Whether you read from right to left or left to right. Endianness is not related to direction. which the stack goes, in which, all right. Yeah. Okay, that makes sense. So the direction that the stack grows is now related. Indiness determines like whether we read the least significant bit at the lowest or most significant. Or most. Because the is this because the stack goes downwards from high to low edge. Hmm? This is a little Indian. Your lowest address is your least significant bit, isn't that big Indian? Oh, the most significant. I'm a little confused. is so is data is are we generally we read from low address to high address or high address? Because stack grows from high to low address. So even though the data is stored as little endian, when we print the binary, we read as big endian, right? When you read an int binary, it's essentially left is lower address. Lower to high. Also, yeah. Yesterday when we were looking at memory, I did something like this: int x equals 5, and then pointer to x is p, and then I would print like p plus 100 and dereference it, and I would get garbage, right? Because when you have a program, remember, it's allocated some virtual memory address space, right? So you have your, imagine it going high to low. You have your stack, you have heap, and then you have like your initialized global data and then initialized global data, and then you have your some global variables, initialized and uninitialized, and then you have, I think, right, memory model, your uninitialized data and your initialized data, and then your actual code or instructions, and so p points to some value in the stack, but you go down, what you increment it, so you might go up, right? But the stack pointer, like p, so this value is directly pointing to the stack, right? Huh. Is p a pointer a memory address that is part stack? Oh, yeah. It's a local variable, and local variables are all stored on your stack. When you create an array, that is also loaded onto your stack, but it might get cached. If you have, else you might have like a heap, and then Yeah, allocating it. Okay. Yes, I actually understand. Okay, so yeah, this p is a pointer to the memory address, and then you print out p. Let's generate the memory, and then dot slash a dot out. So actually, this time you dereference it, and it will be 0. What if it's 1,000? Gen memory. Wow. Can we do it like this? And then you get a seg fault. Is our program this big? Since no seg fault. Oh, which means that a pointer is at least 1,000 times 4 bytes further. But memory addresses the stack pointer at the top where the stack pointer starts are not on program. Isn't that true? Like a program is only allowed a fixed memory range, and the topmost range is the stack, then lower is for heap, global data, and then lowest address. Alright. Is mostly correct. How are there some of this? S? What does that do? Okay. I guess it's undefined behavior, but I don't know why it's undefined behavior. If the stack truly grew downwards, that means that if you do this and you do 2,000, like this should still work. But if you did plus 2,000, then you get a seg fault because the stack goes downwards. So when you go down, there's still a bit more space for the heap, and then you have your global data. Yeah, there's space that's allocated, and probably your heap memory is a lot bigger. I guess it's not that much bigger. I don't know what's happening. 2,000. Oh. Oh, now I'm. Oh. Should be a minus like 7,000. 8,000. 10,000. Wow, it's a lot of space, huh? Yeah, it goes downward. So, which is why when you subtract from it, you go down, that's your heap data. Alright, all this because we were trying to understand matrix multiplication. Alright, this is really fun though. This is really fundamental in terms of understanding how memory works, right? So we were looking at matrix multiplication, and so we have this memory model, right, where our data, you can visualize it, well, we'll visualize it, I guess I no longer visualize it like this. I visualize it as going from oh, here, we'll put it here. By storing the current at when you zoom from a function, the when we resume from a function, the constant, the local variables get restored the registers. We're seeing good bow. How does it know which variables? When you define in C++, you define an arbitrary function, how does the compiler just push the state of all registers to the stack? But like, some say foo has 20 variables in the 20 registers, and then it wants to call bar. Are already stored on the stack, not the register, right? I see. So what did I write here? we push a frame. This frame will contain a series, like a bunch of data. That's how.
Mobile data is on. Let me know if you want to turn it off.
Okay. Is this how this is real world, like in C++? So I need to update current intern. Okay. And okay, we were trying to do matrix multiplication as I was explaining, and we saw sort of our memory model, right? So you can sort of visualize it as your higher addresses are at the top and your lower addresses are at the bottom, and then right, the way that it's organized is you'll have your stack, then you have your heap, then you have initialized data, and your text, right? So when you write a program, any of these programs, that's sort of how your data is organized. So these are your global variables, and these will be allocated on your heap. Or actually, this is not even your heap. This is your global data. It'll actually be somewhere else. Right. Program memory. Is this global data too? Hello? Apart from global data, is there else storage as BSS segment? Where are static functions stored? Is it part of the text or the code section of the memory? Yeah. And sections. Data question mark? I don't know. Huh. I'm not sure. Yeah. And you can look at, alright, and when we call main, we now store the current, right, we're in our stack, and then we make a function call to matrix multiply, and that jumps to, I don't know, some other function in memory, and now it's going to take a pointer. So in this case, these pointers exist, in some part of memory, right, which is your RAM, but you want to load it in because it's going to be cached, and it's going to be loaded into your registers, which are actually going to do the computation through your ALU. So ALU is some logic units, or I guess like CPU, right? You have your CPU, and then there's I guess this, you have your CPU registers, and then your ALU will actually do the computation, right? You can't just like take it from memory and do the computation. But one thing we should be aware is in terms of how big your cache is, right? Reading from cache is very, very fast. Reading from your RAM is very, very slow. So ideally, when things are in your cache, you you can do these operations a lot faster, because the bottleneck, if you don't have a big enough cache, the bottleneck will be in terms of the transfer rate between your memory and your registers, right? Because you need to load it into your registers, and then you need to do the operations and then store it back into memory, right? Which is why, now if we did a much smaller size, so there's so remember, like, so each of in our 64, we're in a 64-bit architecture, which means that each register can store 64 bits at a time. There are also SIMD instructions where you can actually, there are special registers that are very wide, and you can store like 512 bits. But in our case, we're just like doing 64, because we're on a Mac. So this is 64 bits, and where am I going with this? You load it into your registers, you do some operations, and you write it back. So in our case, let's see, we have a 1024 by 1024 matrix, right? So if you just calculate how many bytes that is, that's 1024 times 1024, and then each float takes 32 bits, so that's 4 bytes. So it's going to be 404 million bytes. And you can, how much is Mac L1 cache? How to determine cache? Was that how to find a girlfriend? I just saw how to find a Stanford girlfriend. Oh, that's really cringe. How much is L1 cache? Or how to determine. Okay, I need to delete this. Guys, I need a Stanford girlfriend, okay? How to determine cache size on Mac. So there's a command on this. You do this. So also your L1 cache, there's an instruction cache and there's a data cache. So our L1, so I is our instruction cache, and then our data cache is going to be 65,000 bytes. So that means that if the largest matrix, what's the largest matrix that could fit into our cache? 512 by 512, so that's 4. How much is that? That's too much. What about 64 by 64 by 4? So we have one of those. So if you multiply this by 3, that just barely fits. So if you had a 64 by 64 matrix and you had 3 of these, the total amount of bytes that they would take up is 49,000 bytes. And because our L1 cache is 65,000 bytes, then actually all of the data fits into cache, right? Which means that your access pattern actually doesn't play too much of a role. Okay, so so matrix multiply. So we have matrix multiply v0 and matrix multiply v1, and the only thing that we change here is the order of the access. Right. So as a reminder of how matrix multiplication works, matrix mul. Are you serious? Where's my Excel code drawing? I didn't make a drawing for no reason, guys. Where is my drawing? What's this drawing about? Is this used somewhere? Okay. Hello? Oh my god, this is embedded drawing. So if you look at our matrix multiplication, what we actually are doing is a dot product between two vectors, right? So this vector for one first, or like fourth row times fourth row times third column equals 4 3. Fourth row times third column is equal, the dot product fourth row third column. Yeah, it's a dot product. So this first way is not very cache friendly, but I'll show you that it doesn't matter. So let's kick out and let's do like v0, and then a b d, and then this is n, right, and then v1. This is v1, okay? And my prediction is that it's about the same performance. So the only thing that we did in the second is that we're gonna I didn't do it yet. So we're gonna swap this inner for loop with the column for loop. And what that's going to do, I mean, if you can visualize it in the head. It took me quite a bit of time to visualize it in my head. But essentially, this is a lot more cache friendly because your matrix, when it's stored in memory, you don't really store 2D grid, right? Like it's a linear memory model. You can visualize it like this. So you don't really, like, each of these store 64 bits, or like actually each of these store a byte, right? Because we have byte addressing. Things are byte addressed. So essentially what's going to happen is when you want to access even if you do this, but this is actually going to linearize it. Linearized array, right? Things are linearized. So under the hood it will be flattened out. So this is actually equivalent to n times n. And why am I going with this? So now remember, yeah. So if you look at this operation, what this is doing is it's fetching, right? It will do this dot product, right? So for matrix A, it's fine. So it will take the first element multiplied by that first element of the first element of the row multiplied by the first element of the column, and then it'll do the second element of the row, right? But because remember your matrix is stored, like in this direction, right? And then let's strokes out. Your matrix is stored like this. And let's do a line here. How this in right, this is how it exists in memory. So if you read from this first bit, it will actually read if so things are cached. Okay, so if you read you try to read some data from memory and it is not in the cache, it will cache it, and it will actually cache 64 bytes at a time. Caching. Well, it will read one cache line. So if you read, I did ask ChatGPT this today or yesterday. 64 bytes. You imagine you have int 64. If you read x0, the your computer actually reads a full hash line, so it will cache 64 bytes. In this case, since each int is 4 bytes, you have long or double. So since each double is 8 bytes, it will cache bytes values to x7. Correct? Yeah, this is definitely correct. Memory alignment. Huh. Okay, so what I wanted to explain was it would cache, right? So you read row 0 and column 0 with inner 0 type 0 0. So your matrix, I have to go back every time, right? You multiply your first, oh my god, what's going on, right? You multiply your first row by your first column to get your first element, and because, so you try to get this element, and it's a cache miss because obviously you've never read from it, and it will actually cache this entire, well, it will cache 64 bytes, right? So whether you go up like 64 bytes, however many elements you have. But in a context, in a case where you read from a column, so actually when you read from a row, right? Like in our case, we have 64, a row is 64 different elements, right? And each element of float is 4 bytes, right? So 4 bytes divided by 64 divided by 4 is 16, right? So you actually cache 16 elements. So for a row read, you're actually going to do 4 cache. It requires 4 cache line reads, right? But for a column, so read from this, right? Every 16 elements, you'll have to redo a read from your cache line if it's not cached already. And then for your columns, the thing is you have a cache miss on the first row, then a cache miss on the second row, right? Because your cache line only spans 64 bytes. So every time, so for this first time, you have a cache miss every single time on the rows. But I'm saying that it's fine if you have 64, because once you have this cache miss for all the rows, because your like your total amount of rows is not that many. Once you get to here, like maybe a good way to visualize this is like, let's say caching, right? And then let's imagine this is like, and then let's do this, right? So imagine you do a read from here. Then your computer is going to cache these values, right? And then let's do a rollout. So we read from A, right? And then you read 0 0 from A, and it's a cache miss, so it's going to go and read in from memory, load it into the cache line, and then your first, in this case it would be 4, but like it would be 16 values, right? 16 values because that's 64 bytes. Each value is 4 bytes. So then you read from A, that's stored in your cache, and then you also have a cache miss for your row, right? So then you cache it in, and the problem now is for the next element. So this second element is cached because it is part of the same row, but because you store your data in a row major way, this element is not cached. So now you're going to do another cache read, or you have a cache miss, and then you'll read from memory and then recache it, right? So you can see that this process, for if you store it in a row major way, you only have a cache miss. It'll be 4 times, right, for 64 with 1, but like in this example, yeah, like you'd have like this would carry over here, but this you need like you have a cache miss basically on every single new row that you're reading from, right? So every single inner value, it'll be a cache miss. But it's not as bad because once you do this, you right, like the next time, like for the second column, now all the values are cached, right? And then you won't have a cache miss again, right? And then the only afterwards, after you read 16 elements, or like you get to this 17th column, then you have a cache miss again, and then you do that. But it's actually not too bad because these matrices, all of it can fit into cache, right? So it's negligible. But now imagine the case where you have a super big matrix, and you can imagine that your column, like your matrix is so big that it can't fit all into cache. So what's going to happen is that at some point you're going to read these columns, like even for the first, right? Like you can maybe imagine that the matrix is so big, like imagine a 1024 by 1024 matrix, right? You're going to, so how would that work? Like you have 1024 rows. So already 1024 rows, and each cache line read is 64 bytes. And then how much is that? That's already 65,000. Yeah. So your cache line would already be full, right? Like I guess it would fit all. So you read one, so you read from A, and then that's one cache read of 64 bytes, and then you read, and then for the last row, at this point, like you already are out of, like, your cache is full. Your L1 data cache is full. So what's going to happen? Let's say it's like the least recently used policy. It will clear this cache, and then now this will be cached, right? And then it's going to be fine. And then you store that. You add these values up, and then store it into there. Okay, so that's your two reads, and then you read and you add, and then this is also probably cached, I think, right? Because you read from it and you increment it. So this is also cached. So actually, like okay, yeah, this is also cached. So you actually run into this issue. I think it will be like this, and then actually, so I think this gets removed, and then you end up like this. So once you get to here, like this will be here, and then this will be here, right? Like this cache is clear because your cache line is full. Your L1 cache is full. So you can see that, like, the next time you try to do the second column, now, like, because we don't have that much of a cache, like our cache is not big enough, again you're gonna have a cache miss. So you have all this performance drop off because your cache is too small, right? We didn't have this issue when our matrix was quite small, and all of the few matrices could fit entirely in our cache. Okay, so now we're going to illustrate what I was trying to explain. So if we just have a very small matrix, and it's a 64 by 64 matrix, and I probably need to explain this better again, but auto start. Okay, so the start elapsed. What, 0 millisecond? Are you serious? Okay, I guess we can do. I mean, it doesn't really matter. Like, all of it will fit into cache. Huh. 95. Wait. Am I doing this right? V1. Start is no. Is there some compiler optimization going on? G++. Guess we can do. And then object dump men dot disassemble. And I think, oh, a lot. This is a lot. Is there like a v-add? Don't know how to read this. I think there's some compiler optimization going on. The second time the time is 0. Is it? Am I tripping? Start and wait. Oh my god, I'm stupid. I'm so stupid. Okay, this. What am I doing? Okay, 107 and 0, like probably the first time it's cached, and the second time it's not fair. That why is the second time faster though? I guess like for it to be fair, you call it first time and then that will be cached. Don't understand why the second time is faster. I'm confused. It's the same function. Like it's cached. There's some branch prediction going on, I guess. I guess you can see it's approximately the same. There's some flakiness to it. Maybe we do like 1,000. That would be better. Yeah, okay. I guess like by factors of 10, you see it's like approximately the same. Okay, but now I guess we can do divided by n. No, that's not a good idea. I want to show you 512, and then this one is const expert attempts goes to attempts. Alright, and I'll run it once just so it can be cached. So then it's fair as a baseline comparison. So the second time should be much faster. So you can see around a 2x speed up. And this doesn't really matter. You know, if you call v1 first and v0, you'll see that the first time it'll be 500 and 900. Right. So you can see that there's a lot more speed up just by switching the inner and the column loop, because now what we're doing in the second attempt is instead of multiplying, so this is caching, I guess. Instead of multiplying the row by a column, what we're actually doing is sort of we're doing like a row times row. So, but instead of just updating the row column, we're actually doing like updates like this. And then you're gonna go back here, and then you're gonna do this, and then you're gonna update like that, and then you're gonna go down a row, and you do updates like that. And so you'll still have cache misses, right? But now you're doing like a row read. You're reading from a row as opposed to reading from, or like reading from columns of the same row, as opposed to like reading like this. So this is like way more cache aware, right? So that's like a very basic technique to do some speed up. But I think this is way too slow still. I guess we can look at Python, or like let's do some Python real quick. And let's just generate a equals numpy.rand as np, and then n equals 1024 and by n, and then attempts equals to no equals time a b a at b, and range attempts c equals a at b, and then this is random.rand, right? Yeah, I always forget, you don't pass a tuple, you just pass it like that. Is this in millisecond? Yeah, 0.47. So yeah, they can do it for 1024 twice. That's 29 milliseconds. So if we do it once, that should be 15 milliseconds, 20 milliseconds, 22 milliseconds. Still very, very impressive. Whereas, you know, for us, 1024 by 1024, let's say one attempt. How long is that going to take us? And this is kind of cheating. We should not run it once before. It's taking us, what, 2 seconds? And this should be, V1 is 1 second. What's going on? V1 should be faster. No. Okay. Yeah, 2000. So V1. So we're still very, very, very slow. And the reason is under the hood, there's NumPy actually can multi-thread. So NumPy under the hood I think it uses pthread or something, right? And so I think they use, there's like vectored instructions. Does NumPy use vectored? So they have BLAS. Yeah, SIMD makes use of SIMD instructions. So SIMD is single instruction multiple data, right? So I kind of mentioned this, but you essentially have these like long registers, like AVX512 is a 512-bit register instead of a 64-bit register. So how much is that? Like 4 times longer? 512 divided by 64. 8 times, oh, what am I saying? 8 times longer, right? And so with that, you, instead of like computing 8 times, like let's say it's a double 64-bit, instead of like doing it 8 times, right, sequentially, you can just load it all at once and then multiply 8 at the same time. So that's how you get like this 8x speed up. But I think before we even stop here, like there's more speed up to be done, right? Nobody uses Intel breaking that channel was CPU ID. I don't know what this is. So they actually get cache aware. I wonder if I do dash G++, that's stood dash O3. One, two, wow. We get down to 83 milliseconds just by doing an O3 flag. So just with some basic compiler optimization, and if you do this one, see, the compiler can actually get pretty smart. I assume the difference is like they have some this one calls vector instructions. Dash output main dot o, and then object dump main dot o. Disassemble. Length error. What's this? Compare pad and compute. Huh. See the fmad. This is a fuse multiply add. Floating point multiply add. So is this, but this is not vector, right? So this is adds. So adds, so you multiply and add, so that's FMA. I don't think there are vector instructions here. And then floating point mul, floating point add. Is there a way to get it to do our is v add available on Mac? Vector addition. Vector addition. Like v add does. Int a16 b and c at I equals ai plus bi. Gen v add, or like v add v add. Keep forgetting to disassemble. expect some sort of vector to add. Okay, calls ran a bunch of time. And then load, move. Maybe this will be good enough. Add RP. This is yeah. Apple should also have SIMD instructions, right? Yeah, it unrolled the loop instead of jumping in and compare it. Okay, maybe we need to do 64. Or actually do double. What if we did 64, 64? Hmm. I still don't see vector instructions. I'm a little confused here. I'm a little confused. Where is the vectorization? Wait, I'm so confused. Did it unroll it? Is that why? I mean, you have text. Might have just been unrolled 64 times, you know? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 8, 9, 10. Why is there 11? 12, 13. Not RP. Yeah, I don't think this is vectorized. Hmm. confused as to why it doesn't vectorize. Yeah, I am confused. I am confused. Oh. Load repair registers. So I guess if I remove this, then this is just like doesn't, because none of those values are used. Like object dot 4s. Yeah, this is fi dot 4s. So I think that is what is happening when you do O3 main.o8 and then object dump dash d main.o. At least like that's 4s more. Yeah, this is calling so the vector instructions are here. fmol.4s, and so this one makes use of SIMD instructions and gets us to our 83 millisecond runtime, just by making use of like SIMD instructions. And I think that's also what this guy got. Cache aware plus some optimization. You can do tallying. Cache aware. I guess you want to You can do multi-threading? I don't know what a gem is. General matrix multiply. How do we multi-thread? Oh, you just have pragma flags, and then that will call it. That will just multi-thread it. I see. That sounds pretty cool. Does that get us to basically NumPy level performance? Did he get to NumPy level performance? Huh. Okay. Oh, they actually use copper Smith Winograd. So I guess we need to learn. You can try open NKO. That's kernel. Whatever. Huh. Eigen versus NumPy speed. This is really cool. Context menu? What's the context menu? Yeah, okay, you're gonna push the base pointer and then you're gonna pop Oh. So much to learn, huh? So yeah, this is a something I'm looking into as well. Hope you got armor actually working on this. Polyus. Wow. This guy must be insane. Distinguished engineer. He just like worked 1 year at Zooks. That's kind of funny. Yeah, from higher precision to quantization in the process of transfer of going from a higher level precision to a lower level precision. Alright, I really need to understand transformers. Um, or should I go back to the deep learning book? We actually base rule, continuous variables, for gradient based, overflow, underflow. Like transformer architecture. Bias versus variance is like fundamental. I need to understand this, and I still don't. Or should I look into? Cebullum has like a GPU version. So essentially, there's tiling, and then multi-thread your tiles, and then your GPU. On the GPU side, this guy works where? Anthropic. Dude, I actually might work here. Oh, we do not offer interns. Oh, okay. This guy's drawings are amazing, but it's also 1 a.m. Can I think without box as tiling? To the kernel. What's a CUDA warp again? So you would be underutilized. Okay, I see. This is so low level. Like, wow, this is getting insane. Okay, I'm gonna call it here for today. I think I made some good progress in terms of understanding deeper how our computer hardware works. I think we need to go back more to the math and the transformer architecture. I think I went really deep. I still haven't fully finished understanding how do we do really, I guess, like making matrix multiplication super duper fast. I mean, we got to like 80 milliseconds, which is still 10x slower than NumPy's implementation, or at least, is that true? NumPy's implementation is 23, so I guess like 4x slower. So there's still quite a bit of room. I think if we do threads and we do using OpenMP and then you tell it, you probably have like very similar performance. But the main, I think, being aware of how cache works, and then under the hood it's being optimized by calling SIMD instructions. That's like where a lot of the speed up comes in, just by doing like /03 or -03, which lets the compiler make use of these vectored instructions. If you didn't do -03, you would not, like there's just this. This is like 2,000 seconds, and then you can check G++. If you don't do -03, and then you object dump, there's disassemble the main file, and you look like it doesn't make use of that add.4s or f@.4s. Yeah, and I'll just show you again. If you do this and then you object dump it, fm multiply and add. Yeah, this is actually a multiply. Wait, oh yeah, because we're in main now. So this does fmla, because it's doing multiply. Wait, why is it doing multiply and add? Oh, because I'm doing matrix multiplication, so it's multiplying these two and adding it to that value. Yeah, that's really cool. Fuse multiply add to accumulator. This is really, really cool. Okay, alright guys, have a good night.